Hi, this is Alex from devstories.eu. PyTorch Fundamentals, Episode 3 of 18. A single underscore in your code can save gigabytes of memory, but it might also silently break your entire neural network. Knowing when to use that underscore comes down to understanding tensor operations and memory. Consider a practical scenario. You have three separate feature vectors representing text, audio, and image data. You want to combine them and multiply them against a weight matrix. By default, PyTorch creates tensors on the CPU, but for heavy matrix math, you want to use a hardware accelerator. You can check if a GPU is available using the framework's built-in checks. If it is, you move your tensors by calling the to method on them. You pass the target device name, like the string CUDA, into this method. PyTorch then copies the tensor from system RAM into the dedicated memory of your graphics card. With your tensors on the right hardware, you need to combine the three separate feature vectors into one. You do this using the concatenate function, commonly written as cat. You pass it a list of your tensors and specify a dimension. If you combine them along the column dimension, your three narrow tensors are joined side by side to form one wider tensor. You now have a unified input residing in GPU memory. PyTorch handles over 100 different operations, but arithmetic is the foundation. To process your combined feature vector, you need to multiply it against a weight matrix. You can use the matmul method or just use the @ symbol as a convenient shorthand. This performs a true mathematical matrix multiplication, calculating the dot products of rows and columns and returns a completely new tensor containing the results. Sometimes you need element-wise math instead. Suppose you want to apply a binary mask to your tensor, forcing certain values to 0. For this, you use the mul method or the standard asterisk operator. This does not do matrix multiplication. It simply multiplies the first element of tensor A by the first element of tensor B, the second by the second, and so on. Every time you run operations like matrix multiplication or element-wise addition, PyTorch allocates fresh memory for the result. When you operate on millions of parameters, this rapidly consumes your available hardware memory. This is where you have to pay attention. PyTorch provides in-place operations to manage memory overhead. Any operation that ends with an underscore operates in place. If you use the standard odd method, you get a new tensor. If you use the odd method with an underscore, PyTorch directly overwrites the values inside the existing tensor. The memory footprint stays exactly the same. While in-place operations are highly efficient for memory, they are also dangerous. When you overwrite a tensor, you erase its previous values. Neural networks rely on a complete record of past states to calculate derivatives during the learning phase. If you overwrite a tensor using an in-place operation, you destroy the computation history the system needs to update the model. Reserve in-place operations for formatting data before it enters your model, and stick to standard operations during training to keep your computation history intact. That is all for this one. Thanks for listening and keep building.